Thank you, Mr. Lawrence, for your nice introduction. So, am I audible and my slides are visible? First of all, let me thank the Thieme for giving me an opportunity to give a presentation in this webinar. And I know that the series of webinars are going on in a very interesting way, and a lot of our participants are there. So it is my privilege to be a part of this webinar. So today I am going to talk about the NIR fluorescent probes for the detection of targets. Though there are so many targets are there, in today's talk I will be particularly focusing on chemical warfare agents. So from the fundamentals of sensing to application in detection of chemical warfare agents, I will be focusing on today's lecture. These are all my contents. So let me give a brief introduction about what is meant by supramolecular interactions and what are the chemical warfare agents and what is the scope for the current research. And in addition, I will be focusing on some of the 3 important probes, NIR-based probes that we have developed in our research lab, which shows a very good sensing for the chemical warfare agents like DCP, phosgene, and they have a very good detection limit also. And I will conclude my talk with acknowledgement to my group members. So supramolecular chemistry is chemistry beyond molecules. Normally in molecular chemistry, it will be more of a covalent bond formation. Here it is mainly based on the non-covalent interactions like ion-ion interaction, ion-dipole interaction, hydrogen bonding, anion or pi interaction, and so on. So these are all weak intramolecular or intermolecular interactions, which will be mainly useful in the form of post-guest chemistry. So here we will design molecules which can have a supramolecular interactions, and they can have a self-assembly when an external guest or an external target come into picture, and this binding event will be emphasized in the form of a color change or a fluorescent signal, turn on signal, or there will be some optical output. So normally it involves like dynamic covalent chemistry, and these supramolecular interactions are very easy to form, and then they are also easily reversible. So that makes it more application oriented, because in the presence of the stimuli there will be an interaction, and then there will be an fluorescence output. When the stimuli is removed, then it will go back to its original position. So we have they are all very dynamic, so it is defined by a kinetic and dynamical properties, and we can design the probes, and we can plan in such a way there is a push and pull strategy or a lot of conjugation involved, so that they will have the output in the NIR region. So NIR dyes are very important when it comes into application like fluorescence imaging. When you go for a bioimaging, which is a non-invasive one, the dye has to be in the, if it fluoresces in the NIR window, it will have a deep tissue penetration, and then it will minimize the autofluorescence. So these are all some of the advantageous aspects of NIR dyes. So there is a far red region, and then near IR region, and near IR2 window is also now there, where we can make use of the nanomaterials with the H and J aggregates to have their fluorescence in the NIR2 window. So we have designed some molecules which with an extended pi conjugation, and then with a push-pull electronic framework, so that in the presence of an external stimuli, they will come and assemble, and then they will form a new one which will fluorescence in the NIR region. So the intermolecular forces, as I said, they are generally weaker than the covalent bonds, so they can be kinetically more level, and thermodynamically they are less stable, but they can be always they go back to their original position. So the reusability of the probe for the detection of the targets will be very high. So these are all some of the important interactions. Out of these, the hydrogen bonding and then the anion pi interactions are going to be very much useful. So the hydrogen bonding interaction is mainly used in the detection of anions or in the formation or in the interaction of the chemical warfare agents, and they can be, and when it comes to even solvent will have the interaction with the receptor molecule, and you can detect the presence of polar or non-polar solvent due to the solventochromosome. So the hydrogen bonding is having a lot of potential in the supramolecular chemistry, and this anion pi interaction is also there. Why, if we go via the strength of the interaction, the hydrogen bonding can be weak or strong, and the ion-ion interactions are very strong in the order of 200 to 300 kilojoule per mole, and the ion dipole is moderately strong, and dipole is very weak, and this anion pi interaction is an energetically favorable for the detection of the guest molecule like anion, or small molecules like glucose, or even nitroaromatic explosives, and so on. So why supramolecules is the ease of formation. They can be easily designed and synthesized, and they are very much adaptive. So only in the presence of a stimuli they will form a assembly, and when the stimuli, external stimuli is removed, they will go back to the original position. So that is the importance of this, and it can be reusable many times. Like this, an elastic nature. If the external thing is removed, it will go back to its original shape. Similarly, the probes that can be designed can always go. It can be reused many times. So these are all the advantages of designing a supramolecular probe for any host guest chemistry. So though there are so many reports are available, still there is a scope for improvement, because most of the probes that are reported so far, they have a very less solubility in the aqueous medium. Most of the work is done in the DMSO or in the aqueous acetonitrile, or a lesser percentage of water, like that. So designing a probe which can be completely soluble in water is more advantageous. And some of the probes involve a lot of steps are involved. So it is a complicated synthesis. So for designing one probe, if it has to go through some 8 or 9 steps, means even if it is very good working, it may not be commercially applied. So complicated synthesis, and they take longer response time. So in the case of sensor studies, selectivity, sensitivity are more important. So selectively detecting one guest species among n number of other molecules is very important, and also how fast it responds to that analyte is very important. And limited applications, because they work in the solution level. When it applied for a gaseous phase, or when it comes into the device, they may not be useful. So they have a limited application, and sometimes they have a very poor selectivity. They sense, for example, trivalent cations, means any probe that designed for that will detect Al3+, chromium 3+, and Fe3+, all trivalent will be sensed. So there is no selectivity. And quantum yield, and finally when it comes to application in the bioimaging, they do not have that much resolution. So these are all some of the drawbacks that still have the places where the researchers can focus on and design new molecules to have a better aqueous solubility, lesser steps in synthesis, which will have a very fast response time and practically applied, and which has a very good selectivity and a good resolution. So this I am saying just to show that there is still scope for improvement in any field of research. So as there are so many targets can be detected, particularly we are focusing on chemical warfare agents, because they are very dangerous and then toxic. And in defense area, the application for warfare agent detectors is very important. From the World War II, only these modern chemical warfare agents were coming into picture. Generally, they were classified as G agents, V agents, and so on. So G stands for German, because it started first in the German. And these chemical warfare agents are highly toxic, and then they are very difficult to sense also, whether it is present in the atmosphere or in the soil, because in the warfare area, how if very less concentration if it is there also, it can cause a greater damage. So it is very difficult to sense, and they interact with the human nervous system and the lungs, and they will cause the death very fast. And some of the warfare agents are persistent, that they will stay in the atmosphere for a longer period. Some are semi-persistent, some are non-persistent. So according to their these characteristics, the classification of warfare agents is also very wide. So persistent agents, they are classified as H, G, and B, and non-persistent is fast G, and semi-persistent, some of the G agents are also coming. And these are all the commonly coming nerve agents like sarin, soman, tabu, and DCP. And we don't have the physical access to sarin. So in the lab scale studies, we will be using the mimics of these chemical warfare agents. We will use the dichlorophosphate, diethyl chlorophosphate. This is DCP, which is like a mimic for this sarin. And phosgene, we will take triphosgene, and then in situ we will generate phosgene, and we will use it for the detection. And these are all the commonly called as nerve agents, because they will involve in the central nervous system. With we have an acetylcholinesterase enzyme, which will be, so these nerve agents will act as inhibitors for the acetylcholinesterase, so that it will block the further reaction, and it will affect the system. And these phosgene is called as a lung injurant, because it will go into the alveoli of the lung, and it will cause the asphyxia. And based on the structure like organophosphorus, mainly in the case of pesticides, only first these things came into existence. Later on, it was found that these are all very bad, and some places it has been banned also. Nitrogen mustard, sulfur mustard, and so on are there. Here, there are few lesser dangerous ones which are used to disperse the riots, like in the tear gas and all. They are also comes under the category of chemical warfare agents only. So this is how the sarin will function. So it will bind with acetylcholinesterase enzyme, and it will stop the functioning of that. And this lung endurance, this is a normal healthy lung, and they will go and block the alveoli and with the mucus, and finally they will cause the death of the person. And there is a permissible limit for all these things. So based on that, the probe has to be designed in such a way that it has a very good reduction limit. So highly, the exposure limit of phosgene is greater. If it is more than 90 ppm, it can cause the human death. So lesser than 90 ppm will lead to some complications. So any probe design should be able to detect the presence of these in a lesser than 90 ppm level. And normally the supramolecular interactions like hydrogen bonding, the receptors, if they have this, the phosgene can be come and disturb this, and then it can lead to a fluorescence turn on or turn off. So that was a strategy behind this, to devise a probe for these type of chemical warfare agents. So the advantages of this probes are, we can get a color change output which can be observed by the naked eye, and they can be highly sensitive. So you can have a very good detection limit of nanomolar or picomolar or femtomolar, and they are highly selective also. Even in the presence of any other many interference, it can selectively target one of the chemical warfare agent, and they can be easily coated onto strips and may be used as devices. And you can do both quantitative as well as qualitative analysis is possible. And one receptor can be tuned in such a way for detecting different analytes. So you can play with that So there are a lot of advantages for this probes. That's why we are focusing on developing more of NIR based probes with a simple synthesis strategy. So the first work that I am going to discuss is about a covalent assembly triggered. So here this covalent assembly is a push-pull electronic strategy will be in a die, and then in the presence of an external stimuli, the two parts will be come together and then it will complete the conjugation. So as such, the starting material, the probe will be non-fluorescent in nature. In the presence of the target analyte, this conjugation will be completed and then it will be highly fluorescent. So why DCP is taken as a serine mimic is it can be from thionyl chloride or oxalate chloride. You can do a reaction and then by a halogen exchange reaction, you can easily form the serine. So these diethyl phosphenyl chloride and or diethyl chlorophosphate are considered as a mimic for serine, and normally we don't have access for serine. So whoever does research on chemical warfare agent, normally they will select DCP as its mimic, and if the receptor is sensing DCP means it will also sense serine. That is the fundamental theory. So based on that only, we have also selected DCP, and we have designed the probe for selective detection of this DCP. So this is the example of a covalent assembly. So this was first found in around 2014. After that, only 2-3 reports are available on covalent assembly. So there is a push-pull strategy involved in this. So here now you see the conjugation is not complete, but in the presence of DCP, this conjugation will be complete, and then the electron flow will be from one end to the other. So as such, this dye is non-fluorescent in nature, and by the presence of an external stimuli, this is triggered and the conjugation is complete and it becomes a highly fluorescent in nature. So this is one example which is known, and this is the receptor that we have designed in our lab, and by making use of diphenyl melamate with NN diethyl hydroxy benzene, we made this cyclization, and then by Wills-Meyer formulation, we got this. Then the another equivalent of this is introduced here, so that similar to this NET2, you have the electronic push-pull at both the ends of the molecule, and this is the place where the conjugation is now incomplete. So when the DCP comes here, then this conjugation will be complete. So this molecule originally it will be non-fluorescent in nature, and in the presence of DCP, this conjugation will be complete and it will become fluorescent in nature. So with that idea, this molecule was synthesized and characterized. So completely it has 100 nice peaks for all the necessary protons came, and the compound is characterized by high resolution mass also, and everything matches with the expected number of peaks. So when it comes to the selectivity studies, we take all the possible interference, like what are all the chlorine containing one, like HCl, thionyl chloride, tosyl chloride, fast gene, and then DCP and MEOCl. Out of these different, only DCP alone showed the color change, also in the highly fluorescent. You see there is a, when it was excited at 550 nanometer, and then the emission came around 658 FR rate to near IR region, and it is all other interference do not have any reaction. Only DCP could change the fluorescent nature of the probe, and it is also very fast. Just by the addition of 20 micromolar of this, the fluorescence intensity abruptly increased. So it is a very rapid response, and then it was saturated after that, and selectively it could give the reference for DCP. So the mechanism is like this. So this is the probe, and when the DCP was introduced, the electron flow is from one end to the other end, and then the cyclization is completed, so that the covalent assembly will make the molecule fluorescent. So here the two parts of the dye are now not connected, and only the presence of DCP initiated these reactions, and then this completes the conjugation. So this is a covalent assembly triggered mechanism one, which gives rise to the highly fluorescent, and the fluorescent, this conjugation completed one shows a molecular weight around 391, that this confirms that this expected mechanism is operated in the presence of DCP, and then the product formed was characterized by proton and HRMS. So even in the case of vapor phase also, these are all the test strips coated with the probe, and when it is exposed to the DCP vapors, within 5 minutes, the cyan emission is shown, and with the different other analytes, there is no change, only DCP is giving rise to this. And normally in warfare field, the traces of this DCP can be in the soil, sand, wherever the place. So even when it is in the heterogeneous medium also, whether our probe could work or it will work only in the aqueous medium or only in the solution phase. It's not like that in solid, in vapor phase, as well as in liquid phase. In all the three phases, whatever the trace amount of DCP is available could be easily detected with a very good fluorescence intensity, and it has been applied for cell imaging also in the case of HeLa cells. So it gives a nice red fluorescence with the emission range of 658, and if still the NIR window is, it is only for near IR, it's not it. If it goes above 700 mils, it will be very perfect one. So this is one such probe that we have synthesized. The another one is a cyanine based. Here we have used this cyanine based receptor for phosgene detection, phosgene in vapor phase also. So the strategy behind this synthesis is we have made use of the cyanine. So this indolysine was taken, and then normally the lone pair of electrons in this can attract any of the anion, and they can also interfere. So in order to avoid that, we alkylated that with the iodo-propane, and then from cyclohexanone by a Wilsmeyer formulation, we got this. Then two equivalent. So if it is one side only it is connected, means it is a hemicyanine. Here it is both sides, it is a cyanine. So now the conjugation is very extended and very good here. So it is expected to have a very good emission in the NIR region. And also because of this alkylated one, they have a very good water solubility, and they can give a good fluorescence change in the presence of toxic phosgene. So with all these expectations, this molecule was synthesized, and it is completely characterized by proton C30. So the splitting and then the integration for the expected number of protons are there, and also with the mass spectrum, the obtained mass was an n+1 peak is formed. And when the photophysical studies were done using UV and fluorescence, we checked the sensitivity and selectivity with different probes like SECL, DCP, HCl, POCl3, antosel chloride, and trifosgene. So here we will take trifosgene, and then in situ we will generate the phosgene. So only for phosgene there is a green emission was taking place. And you see the NIR weight is in the 742 nanometer. So the excitation wavelength is 640, and it is in 98% water with 2% of acetonitrile was the solvent. So almost like in a 100% aqueous medium it is working. And this is the incremental addition. So up to 0.6 equivalent, the saturation is attained. So with a very less reduction limit, it can give a very good fluorescence. And it is also very fast. So the moment you take trifosgene and add a little amount of water, then the phosgene will be formed. Once the phosgene is formed, the fluorescence enhancement is taken place. Then you can reverse this reaction by adding triethylamine. So repeatedly, this can go for up to 1, 2, 3, 4, 5 cycles. The reusability of the probe can be done. So the mechanism of reduction is, so as I said, we will take trifosgene, and then either you can heat, or even if you use a mild acidic water, then this through a 6-membered intermediate it will go and it will release the phosgene in situ. So this really in situ generated phosgene will undergo a reaction like this. So two equivalents of the cyanine probe will bound together by this COCl2, and you get a highly colored species. And this can be reversed if you just add a triethylamine. This will be cleaved and you will get back the starting material. So this product in the presence of phosgene is confirmed by the mass. It has been isolated and confirmed by mass spectral studies. So even in vapor phase, up to 30 ppm, it can detect. So less than 90 ppm is a very good reduction limit. And this is also be used in the HeLa cell light cell imaging, and different interference are tested. Phosgene in soil, different soils, and then phosgene in vapor phase, phosgene in liquid phase. Anything can be detected by this probe, and it is having a very good in the NIR region. So the third one is for phosgene. This is based on the excited state intermolecular proton transfer. So here we thought of taking triphenylamine and then imidazole. So our aim was that this NH imidazole proton will have intermolecular hydrogen bonding, and the trifosgene will come into picture. Then this intermolecular hydrogen bonding will be disrupted, and that will lead to the color change or a fluorescence turn off or turn on. So this molecule was synthesized in very good yield. But surprisingly, because of the nearby carbonyl group, there is an intramolecular proton transfer between these NH and C11O. And when the phosgene was introduced, it entered into a cyclization and the new product was formed. So this is the characterization of the probe as such. And this is the photophysical studies. So the probe was lightly pink in color, but in the presence of trifosgene, it became pale yellow in color, and it gives rise to a very good fluorescence turn on with up to 120 micromolars. After that, it attained saturation, and the limit of detection for this probe was in the nanomolar, and the response time is lesser than 10 seconds. So it was very rapid or swift in sensing the phosgene, 30 micromolar of phosgene. So the mechanism is, so what we expected was an intermolecular hydrogen bonding, but it went via a intramolecular proton transfer between the nearby carbonyl and then the imidazole NH. When the phosgene was introduced, it involves into a cyclization, and then the NH disappeared and the new OH was formed, which was confirmed by the proton NMR titrations. And this probe was also useful in both solid phase as well as in gaseous phase and the solution phase. And these are all the vacuum, vapor phosgene treated strips. So they can be, they are just stick onto the top of the vial, and then the slowly phosgene nippers were allowed to interact with the tip on the vial top. Then the color change was very immediate within less than 10 seconds. So these molecules are easily synthesized, not more than 1 or 2 steps. And then they have different covalent assembly or hydrogen bonding interaction, or they form a macrocyclic intermediate. But they are all selective towards the one of the analyte, and they have a very good selectivity, and they don't others, even in the presence of excess of other interfering analytes, only this DCP or phosphine was able to detect. That is the nice thing about these probes. So to conclude, we have taken a number of attempts for detecting the chemical warfare agents like phosgene and DCP in aqueous medium. The strategy adopted was covalent assembly or hydrogen bonding interactions, and they show very good calorimetric as well as fluorescence turn-off in aqueous medium, and they detect up to a nanomolar, that is 0.08 parts per billion, under aqueous medium with a rapid response of approximately around 5 to 10 seconds. And they are all applied for real sample analysis with a very good fluorescence change from red to green, and both solid solution and vapor phase detection is possible. And they are also being applied for bioimaging applications in the light cells like HeLa cells. So these molecules, and we are doing on a variety of other molecules like naphthofluorescein, rhodamine, and so on. These are some of the recent results which I want to share among all of you. So I thank each one of you for giving me an opportunity in this. And I would like to thank all my research scholars who are working in this field. The work that I discussed today is mainly done by Vijay. He recently completed his PhD last week. So the main work was done by him, and there are all the other scholars. So I also thank NITT for giving me the infrastructure for carrying out of research, and all our funding agencies like DST, CSIR, DRDO, and recently we got one Prime Minister Research Fellowship also. And our research collaborator, Professor Shupowu from National Chiratang University, Taiwan, where the scholars have visited 2-3 times, and we also have a SERB OVDF fellowship to visit there. And most of the bioimaging studies were helped by him. So I thank Professor Shupowu also, and I thank all the participants and the team publishers, all the panelists for giving me an opportunity to present our work in this. Hopefully, we will extend our research further in various areas and serve to the mankind. Thank you all.